So, a couple examples. I think today that's the next step is examples of how to use this stuff of linearization, right? So, what I did for today, I went through the notes from yesterday and I just kind of highlighted the three big equations that you're going to use for this, right? So one of the things you're going to be asked to do is just find linear models, write the linearization. Well, there's the very first page we talked about yesterday. This is stuff we could have done before we even started, began this section. That's it right there. That's the equation of the linearization, the tangent line that's going to model the function, right? L for a line, L of x equals f of a plus f prime of a times x minus a, where x is the input value, right? And a is the value of x that we're using for our point of tangency, right? Okay, so there's one. There's uh, there's kind of the other one we're going to use, which is the equation of the differential, right? The differential dy is just equal to, really it's equal to f prime of x times dx. But if we're specifically looking at like trying to model some kind of a function, usually we'll call it f prime of a, where again, a is a convenient value of the input, okay? And we looked at some examples, a couple examples yesterday where we actually calculated some derivatives in differential form. Okay, and just some, these are from our textbook, so I just threw those in. Okay. Just a little visual representation of delta y versus dy, right? Delta y is the actual change in the function. Dy is the change in the tangent line that approximates the function. And these are both produced whenever we bump the function one way or the other, the input one way or the other a little bit, right? We're going to tweak, we're slightly perturb the input. That's what we'd say. We're going to perturb the input value. We're going to slightly bump it one way or the other and see what the response is to the function. Okay, the amount that the function actually changes delta y, the amount that the approximation of that, the amount that the tangent line changes, the y values change, we call dy. Okay, and again, dy is just f prime of x dx. That's it. Okay, and then this is the third equation, and that's it. And this is just a restatement of the first one, right? We can just say, if we'd rather, like if we're thinking about this in terms of a bump instead of inputting values of x, then instead of writing x minus a, we'll just change that to dx. Okay. Depends on how you're looking at this. Are we trying to just find the equation of a tangent line where we're inputting values of x? Then we use the blue version. If we're specifically thinking about tweaking this by bumping it a certain amount from its starting value of x equals a, then we'd use the top one. Okay. All right, so let's look at some examples. What about one like this? Write the equation of the line that represents the linear approximation to the following function at the given point a. So here's our function, f of x equals 7 minus 3x squared, and we're picking the value of a to be 3. Okay, so what are we going to do? What's our equation we're going to use here? It just comes from point slope is all, right? And I hate to have you memorize equations. Like if we start with point slope, what's point slope? Okay, and if we just solved for y by adding the y1 to the other side, right? Something like that. Okay, so what's that become for part A, for our linearization then? This is the equation of the line, right? So we would replace y with L of x, if we want to write it in function notation. Okay. What is y1? What is it? F of a, right? Because the point of tangency, the point that we know, x1, y1, the x value we know is a, and the y value is just going to be, well, whatever the output of the function is at a. Okay, so that just becomes f of a. What's the slope going to be? What's the slope of the tangent line going to be? Yeah, it's going to be the derivative of the function at the point of tangency, right? Okay, so that's just going to be f prime of a times, whoops, x minus a, right? So that's how we get that equation, right? You can just derive it for yourself anytime you need to. Okay, so for us then, we need to do a little bit of calculation here. So we know a is 3. I guess we need to know what f of 3 is, right? So what's that give us? 7 minus 27, so negative 20. So then that means that our point of tangency is going to be at 3, negative 20, right? And so we'd get L of x equals, well, f of a is what then? Negative 20, okay? Plus f prime of a we haven't calculated yet. We'll get to that. Times x minus, and a we said was 3, right? So now we just need to know what f prime of a is. Well, let's calculate, first of all, what's f prime of x? Negative 6x, okay. So then f prime of a is equal to what? Negative 18. Right? There's our line. And we could simplify, distribute the negative 18 and combine like terms, and we've got our line. Okay? So there's part A. So use the linear approximation to estimate the given function value. Okay, well, we just want to estimate f of 2.9, right? So this is part A. Here, let me just pause there, I guess. I probably went too fast. Questions on that for part A? Okay. Let's look at part B. We'll skip part B. We don't need to do that. Part C. Use the linear approximation to estimate the given function value. Well, we're just calculating L of 2.9. That's it. Just equals some number. Okay, no big deal. Okay, what about part D? Compute the percent error in your approximation. Okay, so let's talk about that. Well, I guess we need to know what the output is then. So what does that give us? right, so in Desmos, it's easier just to define the function than to plug in numbers. Just do L of x, define L of x. Don't even have to simplify. And then I can calculate L of 2.9. And that's what I get. Now, what if I want to calculate the actual value of the function at 2.9? Well, that's easy to do. F of x, using Desmos it is, f of x equals 7 minus 3x squared. So f of 2.9 is negative 18.23, okay? Okay, so there's the information we need to do that last part. We want to calculate the percentage error. I want to do two things here. I want to define two things. The relative error, first of all. So relative error is always defined this way. And I disagree a little bit with what they say here. I don't think you should use the absolute values because it's nice to get a sign in the relative error. If you don't use the absolute values, you actually end up with knowing did you overshoot or undershoot, right? So I don't really like that. They might ask you to do that in the assignment, but just different books and different people are going to look at that differently. But having done a lot of this stuff like professionally and in college and stuff, I'd say I'd never use the absolute values. You can always ignore the negative sign if you want to, but it's nice to know the sign. So relative error. Relative just means, what do we mean when we say relative? We're relating it to something. So we're just going to relate the size of the discrepancy or the size of the error that we made in approximating versus calculating. We're going to compare that to the size of the measurement or the size of the value. That's it, right? Think about it this way. Like if we were, relative error is better than just an absolute measurement of error, right? Because think about this example. What if we were building something and we were going to measure the length of a board and we said, okay, we're going to get that within an inch. Is that good enough? How would you know, right? If we're measuring within an inch, if the length of the board is 6 inches, that's terrible, right? That's a huge error. But if the length of the board is 100 feet, well, an inch might be pretty good, right? So it's always good to compare the error to the size of the value to know, I mean, how does that compare, right? So the relative error then is going to be the ratio of it's going to be approximate the approximation minus the exact value divided by the exact value. Yes. Yes. Okay. Is that what they have? Yeah. Okay, so what about for us then? Which is which? What's the approximate value? Okay, negative 18.2 minus the exact value, which is negative 18.23 divided by the exact value of negative 18.23. Well, what's that give us then? We're going to get what? We're going to get a positive 0.03. Yeah. Divided by, hang on a second here, I got to think for just a second. So if we did over negative 18.23, that's going to give us, yeah, okay, you want to have, that's right, you want to have the absolute value of the exact on the bottom, but don't put an absolute value on the top. Okay. And that's going to give us a value, a small positive value, right? What does that work out to be as a decimal, somebody? Okay. 0.00, say it again. 1645. So we'll just take it out to 3 places. 165. Okay. So what does that mean then? The fact that it's positive is meaningful. How come? Why is the approximation, or why is the relative error positive? Yeah, because our estimate was greater than the actual value, right? So we overshot by a certain amount, and that's the relative amount that we overshot by, right? Okay. A lot of times it's easier to turn that relative error into a percent error. All that means is you're going to take that decimal and write it as a percentage, because it's easier for us to think about things. We work with percent so often that it's easier for us to conceptualize a percentage than just a plain old decimal number, right? So if we convert that, then percent error just equals 100 times relative error. So our percent error then in this case, if I just move the decimal 2 places, we end up with about positive 0.165%. Okay, so our estimate overshot by, less than 0.2% of the original value. Okay, that makes sense? Okay. You make sure, did I get, yeah, I did. Make sure you don't forget those absolute value bars. And of course, if you include absolute value bars in the top, you're just always going to get back a positive number as well, right? So this doesn't tell you if you overshot or undershot. This tells you the percent by which you were off. Okay, and that's what we got, right? Okay, that makes sense? Okay, you want to do one more like that? Okay. So would you want to try it on your own for a second first, or you want to go through it together? Want to take a second? Okay, try it. Try it, and then we'll talk about it. If you want to work on the board, you can, so I can see work, but you don't have to. Does the choice of A, they chose it for you, but isn't that what you would choose? If what you're wanting to do is make an estimate of the value of the function at, it looks like input value of negative 0.03, what's the closest convenient input value? 0, right? So that's why we would choose A to be 0. Okay, let's check it out. Looks like you're done or very close to being done. So first of all, what are the values here? I mean, we need to know what A is. We need to know what, the derivative. We need to know a bunch of stuff, don't we? So what's the value of A? Let's just identify the things that we need to know. Okay, so A is 0. We're going to need to know what the derivative is. Let's think about this one in terms of a bump instead of being in terms of a specific value of x. You can do it either way. But if we think about this in terms of a bump, what's the bump? How far did we bump from A? Negative 0.03, right? So dx is equal to negative 0.03. And dx is just x minus A, right? Does that make sense? Doesn't matter about up. We're talking about x values, right? We're just comparing A to our input value. Our input value is, we bumped it from 0 by negative 0.03. Everybody see that? Okay, you guys probably did it this way. Which is fine. You probably did it this way, where you wrote your linearization equation this way as x minus A, so 0 minus 0.03, right? Okay, I'm just saying now, instead of doing that, I think you'll like this a little bit better. When it's convenient to do, just think about this as a bump of distance dx, right? And what do we mean by a bump of distance dx? We just mean, on this picture right here, we're just going to bump it from the point of tangency to the right or left by dx and see what happens to the tangent line, right? Okay, does this picture make sense here? You guys see what I'm saying? Right? So then when we bump it to the right or the left a little bit, we bump it by dx, we just want to know how much did f of a change, right? The initial value of the function f of a changes by dy, right? Okay, so now just try to digest this way of thinking about it then, right? So if that's true, this is the equation we can start with, which I claim is easier. It's easier to think about. We know that the value of the function at x is approximated by L of x, which is just going to equal the starting value of the function at the point of tangency plus dy, right? What does dy mean? dy is the response to the function of a bump by dx. If we tweak the input, think about the graph, if we bump the point horizontally by dx, here's a good one, right? If we bump this point from A horizontally by dx, we want to know how much did the function get offset vertically? How much did it change vertically, right? Everybody agree? So then, isn't this true? Isn't the linearization just equal to the initial y value plus dy? And what's dy? Dy is just f prime of x dx, but in this case, the value of x is a, right? We know that we're at the slope of the tangent line, right, is determined by the value of the derivative at A. Okay? Give me 1 to 5 on that. I got to know how you're doing on that concept. Not great. Right? That's a little iffy, right? Making that jump. Again, now just let's back up a second. Does this part make sense? If we want to estimate what the value of the function is there, and that's all we're trying to do, right? In this last example, we're trying to calculate the output or estimate the output of the function when we input negative 0.03, right? Everybody agree? So we just want to know the estimate, L of x, is going to correspond to this value, right? That's L of x, right? And 1 to 5 on that. Okay. This is f of a, which is the same thing as L of a, isn't it? Right? Because the linearization, the tangent line and the function have the same y value at the point of tangency, right? Okay, so f of a is equal to L of a, right? Capital L just means, just so we can distinguish between the function and the linearization, capital L means linearization, so tangent line, right? The function corresponding to the tangent line is L of x. So that's L of a. We want to estimate the actual value of the function at x is right here, right? This one, that's f of x, right? We don't want to go through the hassle of calculating f of x. We're going to approximate f of x with this tangent line. So if we start at x equals a and we bump the function out to a new x value, a plus dx, right? So dx is the amount of the bump. Then we want to know, well, how much are we adding or subtracting, if it's negative, how much are we adding or subtracting to the original y value, which we know, that's f of a, right? Make sense? So then that's all this is saying right here is L of x, the estimate of the value of the function after we've bumped it from its convenient value at x, is going to be the initial value of the function, which we know, plus the dy, the incremental bump in the line. And that's easy to calculate because it's a line. That's always f prime of a, which we know or can calculate, times dx, which is the amount of the bump. Slope is just rise over run, right? So if I know what the run is, dx of that tangent line from a, all I'm doing is just calculating the rise and adding that rise to my original value. Okay? That seems a little strange right now, but I promise you, that's gonna be preferable than having to build this line every time. Not that that's such a big deal, but this is super quick once you get used to that concept. Okay. So then dy, we'll write this. Dy is always, that's the definition of our differential, right? Remember we said that yesterday? Differential form of a derivative is just equal to f prime of x times dx, right? Okay. Only because we're talking about a tangent line at a, that's f prime of a. This always gets replaced with f prime of a dx when we're doing a linearization every time. That's what that means. The slope of the tangent line times the run is equal to the rise of the tangent line. Okay? Okay, well, let's calculate this stuff. If a is 0, what's f of a? Yeah, right? E to the 0, anything to the 0 is 1, right? So the output, f of a, which is f of 0, is equal to 2. Okay, so we can start plugging some numbers in. F of a is 2. A is 0, right? So let's calculate f prime. If this is f of x, what's f prime of x? There you go, negative 2 e to the negative 2, or negative x, sorry. Okay, so therefore f prime of a, which is just f prime of 0, is what? Negative 2, right? Okay. So this whole thing right here, we can just replace with a negative 2. And what's the amount of our bump from a? Dx? Negative 0.03, right? Okay, so now we have all the ingredients. Let's do our calculation. So L of x, or L of, really what we're calculating here, I shouldn't even put an x there, should I? That might be confusing. That value we were plugging in was negative 0.03 in this case, right? Okay. So what is this all equal to? Well, it's equal to minus 2 times negative 0.03. Well, that's just positive 0.06, isn't it? Negative 2 times negative 0.03. So we get an estimate of 2.06. Right? Yeah. Yeah. Okay. Make sense? So there's our estimate, 2.0. So that's what we get. So we estimate that 2e to the negative 2.3 is 2.06. Okay. How close is that? Well, somebody calculate this. What is 2 times e to the negative? What is that actually equal to? 1.941. How do we get it backwards? What the heck? Ours should have gone the same way. How come? We made a sign error somewhere. We got to find our sign error. What did we do? Plus f prime of a. Oh. We couldn't have. That seems, yeah. Oh, there's the d. Yeah, there it is. Perfect. That's it. So our dx, our dx is actually positive 0.0. Good eye. Right. That's what it is. Right. Everybody see that? Okay. That's tricky. Yeah. Right. Okay. So this value right here, that's dx. Right. So we got to change this. Our dx becomes positive, and that changes this last little bit right here to a positive, and now what do you know? It works out right. Good eye, Pagan. That's good. Okay, so then we get the value. The estimate is 1.94, which is probably very close. What's the actual value? Okay. All right. Did that help a little bit? Okay.